Introduction to Mathematical Induction. So before we get stuck into mathematical induction, we're just going to look at the factors of 60. And let's list them as following. So let's look at 1 times 60 equaling 60. So we know that 1 is a factor of 60 as well as 60. 2 times 30 also equals 60. 3 times 20 equals 60. 4 times 15 equals 60. 5 times 12 equals 60. And 6 times 10 equals 60. So all of these are factors of 60. But if we look down our left-hand side, we've got 1, 2, 3, 4, 5, and 6, all being factors of 60. And we might be able to conclude that, well, if 1, 2, 3, 4, and 5, and 6 are all factors of 60, that every positive integer is a factor of 60. But as soon as we get to 7, we know that there's no whole number that we can multiply to get to 60. So we can conclude that not every integer is a factor of 60. And mathematical induction is a way to prove that every number could meet a certain set of criteria. So the best way to do this is to look at an example. So let's have a look at this example here. Let's start off with just a simple statement that 1 equals 1. And on our left-hand side, let's add in the next odd number. So 1 plus 3, well, that equals 4. Let's keep adding odd numbers in. So 1 plus 3 plus 5, well, that equals 9. Let's add in another odd number, 1 plus 3 plus 5 plus 7. Well, that equals 16. Let's add in another odd number, 1 plus 3 plus 5 plus 7 plus 9. Well, that equals 25. And by the looks of it, it looks like if we keep adding odd numbers, they actually end up equaling perfect squared numbers because it happened every time so far. But how can we show that this is the case for all the addition of all the odd numbers? And the way we can prove this is true is with mathematical induction. And in order to do this, we need to write a general statement. So let's write the statement that 1 plus 3 plus 5 plus ... all the way up to a general odd number, which we can express as 2n minus 1. We could express the odd number as 2n plus 1, but expressing it as 2n minus 1 takes into consideration the first number being 1, because if you subbed in n equals 1, we'd have 2 times 1, which is 2, minus 1, which is 1, which would represent our first odd number. And we're saying that the sum of all these odd numbers is equal to a perfect square. So we can say it all equals n squared. So how can we use mathematical induction to show that this is true for all values of n? So let's write this statement up here. So we have 1 plus 3 plus 5 plus ... all the way up to 2n minus 1 equals n squared. And we want to know, is it true? So the first step is to show that it's true for our base case. So we're looking for, is this true for all values of n where n is greater than or equal to 1? So our first step is to show that it's true for the lowest value where n is equal to 1. So we're going to, is it true for n equals 1? So if n equals 1, we've just got our first term of 1, and does it equal 1 squared? And it does, because 1 squared is 1. Our next step is to actually assume that it's true if n equals k. So we're going to have 1 plus 3 plus 5 plus ... 2k minus 1 equals k squared. And our next step is if it's true for n equals k, we want to prove that it's true for n equals k plus 1. So we're looking to prove that it's true for n equals k plus 1. So writing this out, we're going to get 1 plus 3 plus 5 plus ... Now it helps to write the value when n equals k, and we know that's 2k minus 1. And then we're going to plus our next value in when n equals k plus 1. So we're going to get plus 2 times k plus 1 minus 1. So we're subbing in k plus 1 for n. And does that equal, we're subbing in k plus 1 for n, so does it equal k plus 1 squared? Now, assuming that this is a true statement up here for n equals k, and we know all of the addition of all of these ones is equal to k squared, which is the same as all of this here. So we can go ahead, and if it is true, that would mean that all of that is equal to k squared. And let's expand this out. So we're just taking our left-hand side and expanding this term out here, we get 2k plus 2 minus 1. So we get k squared plus 2k plus 1. And this is a quadratic that's a perfect square. So we can then rewrite it as k plus 1 all squared, which actually equals the right-hand side. And why is that important? Well, it's important if we assumed it's true for n equals k, we showed that it's also true for n equals k plus 1. And we've already proven true for n equals 1. And looking at this assumption, if it's true for n equals k plus 1, it must be true for n equals 2. But then if it's true for k plus 1 and it's true for 2, it has to be true for 3. And if it's true for 3, it has to be true for 4, and so on. So we've successfully proved that it's true for all values of n. So we can say, therefore, this statement is true by mathematical induction.